Hello, welcome to another module in this massive open online course. So, we are looking at example problems for the DTFT, the discrete time Fourier transform. Let us continue our discussion. Alright, so we are looking at example. Let us start with problem number 13, if I remember correctly. And this problem, let us look at the following LTI system, discrete time LTI system described by the differential equation yn, that is the output, equals minus k equals 1 to n a k y minus k and plus summation k equal to 0 to m b k x n minus k. Now, if you look at this, what we have over here will be, now this is the differential equation for an LTI system. Okay. Now, if this is LTI system, which is a low pass filter, okay, this is a low pass filter. Now, what is the corresponding differential equation or the difference equation for a high pass? What is the corresponding difference equation for a high pass filter that is derived from this low pass filter. Okay. And we can start as follows. Now, taking the Z transform or taking the DTFT, which is very convenient now, as you have seen in all the applications and example problems we have talked so far, the DTFT is a very powerful tool for signal processing, discrete time signal processing. Alright, or discrete signal, you can also call it as digital signal processing. So, we have y omega equals plus k equal to 1 to n a k, a DTFT of y n minus k is e raised to j k omega into y omega equals summation k equals 1 to m, correct, b k e raised to j k omega, I am sorry, e raised to minus j k omega x of n minus k, okay, and this would be, now if you find h of omega, now h of omega equals y of omega. So, this is the transfer function, remember, h of omega, which relates the input and output in the frequency domain. So, h of omega equals well, this is summation k equal to 0 to m b k e raised to minus j k omega over 1 plus summation k equal to 0 to n a k e raised to minus j k omega. Okay. And now to get, so this is the transfer function h of omega, okay, and now to get the corresponding transfer function for but now this is a low pass filter, remember, correct. So, to get the corresponding transfer function of the equivalent high pass filter, I have to shift it by pi, alright. So, omega, so h of omega becomes h of omega by h of omega minus pi, alright. So, we have to replace omega by omega minus pi, okay, and that is what we have seen in the previous example. To get HPF, and this is a neat trick, we have to shift by pi, implies omega becomes omega minus pi, that is we replace omega by omega minus pi, and therefore, h tilde of omega of this high pass filter is summation k equal to 0 to m, or in fact k equal to 1 to m. Let me just correct it, k equal to, this is k equal to, sorry, this is both are both k equal to, these are both k equal to 1, k equal to 1, correct, not k equal to 0, rather k equal to 1 to m bk e raised to j k omega minus pi divided by 1 plus summation k equal to 1 to n a k e raised to j e raised to minus j k omega minus pi, which now you can simplify as summation k equals 1 to m bk, this will be e raised to j k pi, or basically you can write this as e raised to j pi whole raised to k times e raised to minus j k omega. So, that remains as it is over 1 plus summation k equals 1 to n a k e raised to j pi k e raised to minus j k omega. And now you can see e raised to j pi raised to k is nothing but minus 1 over k. So, h tilde omega, the transfer function, which is the transfer function of the equivalent high pass filter, is y omega by x omega, that is summation k equals 1 to m minus 1 raised to k a k e raised to minus j k omega by 1 plus summation k equals 1 to n minus 1 raised to k b raised to k e raised to minus j omega e raised to minus j k omega, and therefore, this implies that if you look at this, we have y of omega into 1 plus summation k equal to 1 to n minus 1 to the power k b k e raised to minus j k omega equals x k summation k equals 1 to m minus 1 to the k minus 1 raised to k a k e raised to minus j k omega, and this implies, now taking the inverse DTFT. So, now you take the inverse DTFT, and this gives rise to the difference equation. You can see yn equals minus summation k equals 1 to n minus 1 to the k y n minus k plus summation k equals 1 to m minus 1 k a k x n minus k. Okay. So, this is the difference equation of the, okay. This is the difference equation of the equivalent high pass filter that is derived from the difference equation and the transfer function for that matter of the given low pass filter. Alright, where we use the trick that to get a high pass filter from a low pass filter you have to shift it by pi or replace omega by omega minus pi in the transfer function. Okay. Alright, let us proceed to the next problem, problem number 14, which is the following thing. So, we consider the impulse response Hn such that Hn equals real. Hn is non-zero only for 0 less than equal to n minus 1, which means Hn equal to 0 for n less than 0 or n greater than equal to n. So, this implies this is non-zero only for 0 less than equal to n less than or equal to n minus 1. Okay. And importantly, Hn has the property Hn equals h of n minus 1 minus n, where n, okay. So, Hn equals n minus 1 minus n. So, this has a symmetry, you can see, if you can see it will be something like, okay. Okay, so this is your 0, 1, 2, 3, it is 0. So, capital N equals 4, okay. So, n equals 4 and so n minus 1 equals 3. So, we have h of 0 equals h of 3 minus 0 equals h of 3, further h of 1 equals h of 3 minus 1 equals h of 2. So, this has symmetry, okay. You can clearly see this has a, and here n is even, okay. Okay, so this has symmetry about this point. So, this is your, you can think of this as your axis of, so you can think of this as basically your axis of symmetry, okay. So, this is basically you can think of this as a as an axis of you can think of this as a symmetry, an axis, a symmetric axis of symmetry, okay. And therefore, this impulse response of this filter is symmetric, alright. It satisfies the property h small n equals h capital N minus 1 minus small n, okay. So, now what we want to do is we want to find the phase response of this quantity theta omega. Now, you look at this property, now phase response. So, we want to answer the question what is the phase response. Now, observe that this property h of n equals h of capital N minus 1 minus n. From this property what you can see is if you flip it, alright, if you basically flip it about 0, this filter about by 0, and if you delay it by n minus 1, alright. In the previous case, for instance, if you consider the mirror image about 0 and delay it by n minus 1, then you get again the same filter, okay. So, flip by 0. So, you observe plus delay by n minus 1 equals same filter. Okay, and this is the interesting property. So, if you flip it over the 0 axis, that is, first you take h tilde n equals h of minus n, that implies h tilde, taking the DTFT, we have h tilde, remember, look at the time reversal. So, we are considering the time reversal basically, time reversal and delay by n minus 1. So, h tilde omega equals h of minus omega, this is from the time reversal property. Okay. This is from the time reversal property, h tilde omega equals h of minus omega. Now, delay by n minus 1. So, we have h double tilde n, which is h tilde of n minus 1, which is basically equals, you can see h of n minus 1 minus n, which is equal to now h of n by the property of the filter. Okay. And from this you can see you have h double tilde of omega equals h tilde of omega, since you are delaying by n minus 1, this becomes h tilde of omega e raised to minus j n minus 1 times omega, okay, which is equal to now h tilde of omega, you can clearly see this is h of minus omega into e raised to minus j n minus 1 omega. This is from the time reversal property. Now, h of minus omega is also equal to h conjugate of omega. Okay. So, h conjugate of omega times e raised to minus j n minus 1 omega, and this follows because h of n is a real filter, alright. So, the coefficients of h of n are real, and for any real impulse response or for any real signal, we know that h of omega equals h conjugate of, that is, h of minus omega is basically the same as h conjugate of omega. Okay. So, basically I can also write this as mod h, magnitude h of omega into the negative of the phase of h of omega, e raised to minus j theta omega, e raised to minus j n minus 1 omega, but this is equal to h of omega from the property of the filter. Okay. From property, because h tilde of omega, because h of n minus capital N minus n, capital N minus 1 minus small n equals h of small n. So, we have h double tilde omega equals h of omega, this is from property of, from symmetry of filter. Which is equal to magnitude h of omega e raised to j theta omega. And therefore, now equating the phase of these two terms, equating the phase, if you call this as term 1 and if you call this as term 2, equating phase of both, equating phases, we have minus theta omega minus n minus 1 omega equals theta omega, implies twice theta omega equals n minus omega. So, this is a neat trick which implies the phase has to satisfy, phase of h of omega has to satisfy theta omega equals half, or this is basically, in fact, twice theta omega is minus n minus 1 omega. So, this is minus half n minus 1 omega. Okay. This basically satisfies. So, this is a linear phase constraint. Okay. So, this is a linear phase. Okay. Phase is linear with omega. So, this has the interesting property that by this symmetry, alright. So, the property, the symmetric property of this real filter results in a linear phase. In fact, that is something that is very interesting. So, the symmetry property endows it with a linear phase. Okay. Alright. let us proceed to the next problem, which is also again very interesting, and it talks about the sampling of, it talks about, this is problem number 15 I think. This talks about the sampling of a discrete time or a continuous time system So, sampling from continuous time system, we have the discrete time system. Okay. So, we have an RC circuit, resistance R, capacitance C, output across the capacitor C, input across the RC serial combination. So, we have the input voltage x t, output voltage y t, and we have seen this several times before. And in RC circuit above, consider RC equals 2. What is the discrete time filter obtained by sampling impulse response, the above continuous time impulse response with sampling duration, with sampling interval So, this is an interesting problem. First, you can try to spend some time appreciating it. So, we have this continuous time system, all right, it is a serial RC filter, all right, which has an impulse response. Now, I want to sample this continuous time impulse response and derive a discrete time impulse response. So, that gives us a discrete time LTI system with a discrete time impulse response. We want to find what is either the difference equation or the transfer function that describes the equivalent discrete time LTI system. Okay. So, basically what is the discrete time filter, or you can say in terms of either the impulse response or the transfer function, and this can be found as follows. Now, we know the difference equation is given as, and we have seen this several times before, y t is the voltage across the capacitor plus from Ohm's law R into I, that is C dV by dt or C dy t by dt, that is the potential drop across the resistance, and this has to be equal to the input voltage, that is x t, which implies that y of which implies that now taking the S transform, y of S plus R C, and R C we know equals 2. So, y of S plus 2. So, given R C equal to 2, okay. So, given this R C equal to 2, that is given, okay. So, 2 into dy by dt has Laplace transform S y S equals x. So, we are basically taking Laplace transform. So, this implies 1 plus 2s into ys equals xs. This implies ys divided by xs equals 1 over 1 plus 2s. Now, this is 1 over 1 plus 2s, this is your h of s. That implies, taking inverse Laplace transform, we have h t equals half e raised to minus t by 2 u t. Okay. So, this is basically taking the inverse Laplace transform. Taking the inverse Laplace transform. Okay. And remember, h n is obtained by sampling this, h n equal sampled okay, with sampling duration Ts. When you sample it, you obtain the discrete time impulse response Hn. So, Hn, now if you look at this, it is very simple, Hn equals h of the continuous time. So, let us do a, so let us call this h tilde n. H tilde n equals h of, to distinguish them, this is h of nts, where h is the continuous time, which implies now h tilde n equals half e raised to minus nts by 2 u n. In fact, that is what u of nts, but u of nts, remember this is e raised to half e raised to minus t by 2 ut. So, this will become u of nts, but u of nts is the same as u of n. So, this will be half e raised to minus nts over 2 u of n, because ts is greater than 0. This is equal to half e raised to minus ts over 2 raised to the n u n h tilde. So, this is the impulse response of the equivalent discrete time system. This is the impulse response of the equivalent dt system. Okay. Now, taking the z transform yields h of z, that is a transfer function, h tilde n is half. Now, this is, you can treat this as half a raised to the n u n, where a is e raised to minus ts by 2. So, h tilde z will be half 1 minus e raised to 1 minus a z inverse. So, 1 minus e raised to minus ts over 2 z inverse, and this is equal to, and this is basically the transfer function of the equivalent dt system, discrete time system. This is the transfer function of the equivalent discrete time system. Now, one can derive the discrete time Fourier transform, the DTFT, by replacing z by e raised to j omega, we know that. So, h tilde of omega now one over 1 minus e raised to minus ts over 2 e raised to minus j omega, or 1 over 1 minus a e raised to minus j omega, where we have already seen a is e raised to minus ts over 2. Okay. And now we can also find the difference equation as follows. So, we have y omega over x omega equals 1 over 1 minus e raised to ts over 2 e raised to minus j omega, which means y omega into 1 minus e raised to minus ts over 2 e raised to minus j omega is equal to x of omega, which implies that difference equation is now given as y of n minus e raised to ts over 2 y n minus 1 equals x of n. This is the equivalent discrete time system. Okay. Or in fact, dE of the equivalent discrete, there is a difference equation of the equivalent discrete time system. Alright. So, we have found the impulse response, transfer function, as well as the difference equation that describes the equivalent discrete time system obtained by sampling the impulse response of the continuous time LTI system. Alright. So, let us stop here and we will continue with other problems in the future modules. Thank you very much.